You guys have a good weekend?
Yeah.
Good, good. So we don't have class on Wednesday, so so our next class in here will be on Friday. We're starting a chapter actually back to the study of fields and waves. So previous chapter we reviewed some vector calculus. Hopefully some of that came back to you from your Calc 3 studies. Homework 5 was due. Were there questions about that? Yeah.
Number 10, the answer is, it says 0, but I got essentially the triple integral of 10x squared, and my answer is 320/3.
Let me look up the problem here. So that's from the supplemental problems.
Yes.
Okay, yeah. Probably good to go through that. So this is the one on the electric flux density, evaluate both sides of the divergence theorem. Is that the one you're talking about, 410?
I'll have to see the question. I don't think that's the one though. I think it's the one about Q.
Yeah, that's it. So given electric flux, evaluate both sides for the volume of a cube, 2 meters on an edge.
Yeah.
Okay. So so this is the divergence theorem. Delta V dV. And D in this, and this is a vector theorem, so it's true in general for any vector field. D in this case is x hat, what is it, 10 x squared over 3. Okay. So, I'll do one side or the other. Did you get the same answer on both sides? Or did you just evaluate on one side?
I think evaluated on one side.
Which side did you do?
The right hand side.
So the del dot D. So del dot D would be is the partial derivative of the x component with respect to x. Right. So that's 20x over 3. And then we have what we're asked to, in this case, it's a cube centered at the origin. So, and I'm terrible at drawing these things, so let me draw kind of the XY plane. And then it would be something like that. This cube, and it says 2 meters on a side, so it's plus or minus x, y, z. Here it's +1. Back here where it crosses, it's -1, and so on and so forth. So this says del dot d dv becomes this triple integral over x, y, and z, -1 to 1, -1 to 1, -1 to 1. Is that the way you set it up?
No, I set up 0 to 2.
Okay.
So
In that case, you would not get 0. Yeah. Yeah. So, and that's fine. No, that for the volume, 2 meters on an edge centered at the origin. So I meant there that instead of having a corner on the origin, that the cube was actually centered at the origin. In which case, centered at the origin, since I'm integrating from -1 to 1 over x, and this is odd, that's why I got 0. But yours, it's fine, you wouldn't. Now the other way to do this, too, whatever you get should be equal on both sides of this equation. So but you do have to be careful here when you integrate. It's just x directed. Okay, so let's take a look at the left-hand side, because that one's actually, this one's straightforward to integrate, as long as you get your cube in the right spot. But again, that's fine. You did the setup of the problem correctly. This one can be a little tricky because we actually have 6 different sides of this cube, the 4 sides and the top and bottom. And so we have to break this down into 6 different cases. So, let's take the top and bottom sides. I think I can. Let me just talk about the top. Now ds there on the top, this is the z equal +1 base, okay? And x and y vary between -1 and +1. But here, an elemental surface area on the top has dx and dy components, but it also has a direction. Okay, it's this surface area, and it's normal to the surface. So here for that plane, it would be either z hat or -z hat. When evaluating the divergence theorem, the surface normal is always pointing outward from the enclosed volume. So on the top, it's going to be pointed in the z hat direction. On the bottom, this is where you have to be careful, students often make a mistake, it would actually be in the -z hat direction. So here it's z hat. On the bottom, it would be -dx dy z hat because of the difference in the surface direction. But here, because d is x directed, this dot product is 0. Okay. Because d is in the x direction only. So it's 90 degrees to the surface. So, and that would be true on the bottom. It's also true on the x equal +1 face and the y and the x equal -1 face. I'm sorry, y equal -1 face and y equal +1 face, because the unit vectors there will be in the +y and -y direction. the back face here, which is at y equal plus 1, would be in the y hat. And then this face at y equal minus 1 would be in the minus y hat. But again, they're at 90 degrees to the direction of our field, which is x directed. So we want to call this, as I've drawn it, we could call this the front, which is the y equal minus 1 face, and the back. So top, bottom, front, and back, we get 0. The only way we're going to get contributions is actually on the left and right side. Okay. So on the right side, ds is dy dz, and it's x hat directed. Okay, the surface element. Is that clear? That's this side. The left side at x equal minus 1, this is the x equals plus 1 side, is going to be dy dx, but in the negative x hat direction. But here, now we get the dot product is actually 10x squared over 3 dy dz. The integral is just over y and z from 1 to minus 1 to 1. On this surface, x is 1. Because everywhere on that surface, x is equal to plus 1 on that right side. So this is actually going to be 2. I'm just integrating over a constant. That would be 2, 2, 4. So I'm going to get 40 thirds. But on the left-hand side, the only difference would be I'll have this minus sign in there. I'll get minus 40 thirds. And so when I add these together, I'll get 0. Now, the point of that problem, and these problems are hard, I know, because there's a lot of visualization involved. Evaluating this alien syntax, it's like hieroglyphics almost, right? These equations, but evaluating both sides there of the divergence theorem to verify that you should always get the same result there. And then there was one in here too on 412 was Stoke's theorem. It's kind of similar. Stoke's theorem has to do with the curl, and then a closed contour on one side, and then the integral of the curl over the surface on the other. So Stoke's theorem is the integral over a closed contour of any field dot dl is equal to del cross A. And here, Stoke's theorem, we're talking about some loop. Okay. So this is the contour, and then this is an open surface now. It's not a closed surface would enclose a volume. Here it's a closed contour with an open surface. That's Stoke's theorem. The divergence theorem is a closed surface, and that means it's all sides, it defines some volume, and then the corresponding volume enclosed defined by that surface. So when you're working with the divergence theorem, it may say something like over a hemisphere. That's a pretty poor excuse for a hemisphere, but half of a sphere. The surface there would include the bottom of the hemisphere. It's not just the circular top. If we're evaluating the divergence theorem, the surface includes that plane that cuts through the sphere. So part of it is trying to understand what the notation here is. But in some cases, like this one, evaluating the right-hand side is actually pretty easy, okay, compared to, it's one integral here. Over here, it becomes actually 6 different intervals for the different surfaces. It depends on the coordinate system. If the closed surface is a sphere and you're using spherical coordinates, it may just depending on the direction of the field, the left side may be easier to evaluate. Okay, we're going to actually review a little bit on some material we looked at back in chapter 1 for statics. And here we're going to study the electric field created by stationary charge. So this is kind of like the DC problem. Well, kind of like DC versus AC. We're first going to look at charge that's fixed in place. Of course, you don't have that with DC, but I mean, it's kind of analogous to, we'll look at electrostatics, and then the case where dynamics, where the charges are actually moving. But here the charges are fixed in place. And we'll also look in this chapter, we'll look at a fundamental definition of capacitance, and then a derivation actually of Ohm's law, kind of from first principles. But back in chapter 1, we started with a discussion of Coulomb's law, which said that the force exerted on charge Q2 by a charge Q1 was given by this equation. This is the force equation. So this is a corresponding picture here. This is Q1, this is Q2, and this vector R is the vector from Q1 to Q2. Okay, so, and it appears in here, remember that that's a magnitude times a unit vector in that direction. So this R, capital R, that appears in the denominator here is really the distance between the two. That's all that is. And then R hat is the direction. So a couple things to note with regard to the force. It depends on the individual charges. If Q1 increases, and let's talk about Q1 because Q2 is kind of our test charge. If the charge on Q1 increases, the force increases. The same would be true for Q2. As the distance increases, the force decreases, falls off with the square of the distance, like gravity. Now, the electrostatic force is many, many, many millions of times the electrostatic force exerted by an electron is many millions of times larger than its gravitational attraction due to the mass of the electron. So we generally feel electrical forces, a lot more than gravitational forces. It also, epsilon here is, our permittivity of the medium. So it is a function of, could be in free space, in which case this would be epsilon 0, or it could be in some side material. Now, somehow you have to imagine at this point that these things are glued in place. Okay, if I had a charge here and another free charge here, they're going to go flying apart. But this would be the force if somehow I had Q1 here nailed in place and brought Q2 and was holding it there, then that would be the force we would feel on Q2. Notice that it's directed away here, it's repulsive. That's if Q1 and Q2 have the same sign. If they're both positive, then Q2 is being pushed away from Q1. If they're both negative, the minus signs would cancel out and Q2 would still be pushed away. But if either one is positive and the other is negative, then we get a minus sign, which means our force would be in the opposite direction. And it would be an attractive force. So what we know about charges, like charges repelling, unlike charges attracting, that's built into this equation. The electric field produced by Q1 is, so what we want to be able to do is talk about, it appears due to the presence of Q1, it creates this force field. So if we bring any other charged object near Q1, it's being either attracted or repelled, okay, depending on the charge of Q1. So we want to be able to talk about that field independent of this little Q2 charge, okay, to decouple these. And so we can do that by actually defining the field due to E1 as, you could define it as the force divided by Q2. So, or equivalently here, E1 is R hat Q1 over 4 pi epsilon R squared. Now, R represents any point, any position vector around Q1. Okay, so now instead of having Q2, this equation applies just to some arbitrary point where R is the vector from Q1 to that point. Okay. So I've defined the field of Q1 all around Q1. We see it's radially directed outward. And the assumption here is we're working with positive charges. If Q1 is negative, it would actually be directed toward Q1 and then gets weaker with distance. So, roughly what this field would look like. And then the field gets weaker the farther we are away. But it's really everywhere here. But it's always radially directed outward from the charge. Gravity has the same form, but gravity is always attractive. There's no such, we don't have positive and negative mass, right? We only have positive mass. So gravity is always an attractive force. The field, when considering a single charge, due to it's convenient to put it at the origin, the field due to a charge Q at the origin is most easily described in spherical coordinates. What I want to build up to is actually what's the field created by multiple charges. But here my R is defined relative to whatever the position Q1 is. Well, I can put that, if I center Q1 at the origin, then that distance vector is just my R vector from the origin in spherical coordinates. And it's, and we could express this in Cartesian coordinates or cylindrical coordinates, but it becomes a lot more complicated. It's easiest to express in terms of spherical coordinates. I want to generalize this though. So let's talk about multiple charges or multiple, we call point charges here. I'm essentially assuming at this point that Q1 has no size. It's an infinitesimal point at some position. And the field at some point R due to a charge Q1 at R1 is, and I really want to generalize essentially this expression I have for the charge created by Q1. So I can do that using my vector notation. So here's X, Y, and Z. And so I have here a point at which Q1 exists. And that vector is R1. It's a position vector. That's the position vector of Q1 relative to the origin. Now I want to find the field at some other point defined in this coordinate system as just R. Okay, that's my field point. Well, from what we know about from this expression, this is what I call capital R over there. And that vector is actually R minus R1 R. That's the distance from this test point to R1, is the difference between those two vectors. Because R1 plus that vector gives me R. And so I plug all of that in. So my notation now here represents, this is the electric field at an arbitrary point in space with position vector R due to a charge at R1. And so I can get R hat. That's going to be R bar minus R1 bar over the magnitude of that vector. Right? That's the definition of a unit vector in that direction. And then I have Q1, and then I have 4 pi epsilon. R squared is, well, it's the square of that magnitude. So the magnitude is R minus R1, again, absolute value squared. So I can rewrite that as R minus R1 over R hat, R bar minus R1 bar cubed, Q1 over 4 pi epsilon. Okay. And again, at first glance, maybe it kind of looks like the field falls off as the cube of the distance. It doesn't, because there's also this distance term in the numerator. Okay. But there's a unit vector embedded in that, R minus R1 over the magnitude of R minus R1. Now, what I want to, superposition here applies. The field at R due to n charges is I can factor out my 1 over 4 pi epsilon out of my, I'm just going to sum up terms like this. N equal 1 to capital N, and I have R minus Rn over the magnitude of R minus Rn cubed times each of the n charges. So it's really just a summation applied to this. Okay, so what this represents is, in space, I've got now multiple charges, Q1 at R1, Q2 at R2, and R is some point in space. So this distance is R minus R2. This is R minus R1. And so I can get the field the electric field at that point by summing all these together. This can be nasty because this is a vector sum, right, of all these different components. I'll work through an example. Often here, some insight looking at some symmetry can help. I think in the homework problems, we'll generally look at 1, 2, 3, a small number of charges here, and often they're positioned so that you can use symmetry arguments to simplify the problem. So let's look at an example. So 2 point charges, Q1 equal 10 coulombs, and Q2 equal, I've got microcoulombs rather, 10 microcoulombs, and Q2 equal 10 microcoulombs. So typically when you start making these symmetry arguments, all the charges will be equal, or you'll have equal positive and negative charges. And then, they lie, in this case, on the x-axis, or they might be lying at the corners of a cube or lying equally spread around the circle at x1 equal minus 2 meters and x2 equal plus 2 meters. And we want to find the electric field in the xy plane. You can extend this problem to actually find it everywhere in space at any height as well. So, but it's helpful always. Here we're just asked to find it in the xy plane. Q1 is at minus 2, and Q2 is at plus 2. And you can kind of get maybe some idea of what the field looks like by, we know that we're going to have these vector fields here radiating outward from Q1 and Q2 in equal strength. In particular, I can see on the y-axis, there's only going to be, above the the y equals 0 line, there's only going to be a y hat directed component on the y-axis. Because this one is pushing that way, this one's pushing this way. They're equal charges, so the x-directed component of the force is going to be 0 on the y-axis. In general, I'm going to have x and y components everywhere. So what you want to do here is actually, pick a test point. We'll use I chose to work this in Cartesian coordinates. So let this be some vector r. So r here quite generally is x hat x plus y hat y. Would be my position vector to an arbitrary point in the xy plane. R1 is minus x hat 2. Okay, that's the position vector to Q1. And similarly, R2 bar is x hat 2. So now I'm going to use this formula, but I'm only summing 2 terms. I can pull out here my charges are equal, both 10 microcoulombs, so I can pull that out of the sum as well. So I'll have 10 microcoulombs over 4 pi epsilon. And then I'll have, this term. For R1, I'll have this minus R1, so I'll have x hat, x plus 2, plus y hat, y. That's the numerator. And then I have the magnitude of this cubed. So what's the magnitude of a vector in Cartesian coordinates? It's the square root of the sum of the squares. So I'll have x plus 2 squared plus y squared. And then the square root of that would be to the 1/2, but then this is to the 3rd power. So it's x plus 2 squared plus y squared to the 3/2 power. So the magnitude gives me the 1/2. And then the 3 in the equation here makes it a 3/2. And then I have a similar term. It's r minus r2. So I'll have x minus 2 plus y hat y, and then x minus 2 squared plus y squared to the 3/2. You can't do a lot with that. The denominator, you can't do much simplification in this particular case. The denominators are different. I can put them over a common denominator. Typically, at this point, you might split the numerator, so I could split out the x hat and the y hat directed components, but it's still a mess, regardless of what you want to do with this. But this is the general expression. I could evaluate this, at different points on the xy plane. Probably want to use a computer to do that. Now, there is this case, though, along the y-axis where this does simplify. Along the y-axis, which is where x is equal to 0. So here I'll have 2 plus y. Here I'll have minus 2. Well, let's look at the x component. If I look at the x hat component with x equal to 0, here I'm going to have 2x hat. Here I'll have minus 2x hat. And in x equal to 0, the denominators are the same, because here I'll have a 2 squared, here I have a minus 2 squared. So there won't be an x hat component. There will just be a y hat component. And I have the 10 microcoulombs over 4 pi epsilon. And here, y plus y with the same denominator, so I'll get a 2y, and then I'll get 2 squared or 4 plus y squared to the 3/2 as the electric field along the y-axis. Now again, the sign is embedded in here. When y is positive, the force is in the y hat direction, upward. When y is negative, the force would be directed downward, when I'm below the 2 points. And that makes sense if you think about, again, the electric field being radially outward, that if I'm below the points, I'm going to be pushed down. I'm above the 2 points, if I'm above the line containing both charges, I'm going to be pushed upward. Okay. And so the sign, y squared here is in the denominator. So the sign is just determined by the numerator y. So this at least is a little more, we could plot this actually, it's just as a function of y to see the magnitude of the force along the y-axis. So still not easy, but it's simplified. You'll notice in some of the problems in the textbook, he might just find the position along the line. What would be the force right here, exactly halfway between the 2 points? Zero, right? This one's pushing to the right, that one's pushing to the left with exactly the same force, as long as they're equal charges. Now, the next step above these point charges is to talk about charge distributions. And again, we know that for us, the smallest charge is the charge on an electron. Okay, so we know charge is discrete, but it's usually more convenient to consider charge as being spread out over a line or a surface or a volume. And we work with these different line, surface, and volume distributions. So in a line charge distribution, we assume that we've got charge distributed over a length. So rho L, and we use this rho to represent with a subscript L, indicating that it's a line distribution or distribution over a contour. And it has units of coulombs per meter. The total charge along the contour would be rho L dl. Now, in a lot of problems we'll work, rho L may be constant everywhere along the line, but it doesn't have to be. Rho L here can be a function of L, the position on the contour. So we can't pull it out of that integral. Generalizing our electric field, going from that sum to an integral, we have a contour integral of r minus r prime, r minus r prime cubed. R prime now is my distance to a test point. R is the distance to a point along the contour. And then rho L, which again may be a function of position along the contour, dl. Actually, let me do it this way instead. I guess that's more consistent. R prime is varying position along contour. And we're going to work a few problems like that in this chapter. And these are not easy. Again, they can be simplified in some cases with some visualization. But one of the things we'll work toward in the rest of this chapter is easier methods for evaluating the electric field than using this integral. The surface charge, we use rho s there. It's charge spread over an elemental surface. It would have units of coulombs per meter squared. we do a surface integral to get the total charge. And then the electric field has really the same form, but now it's a surface integral. Everything else is the same. Rho S, again, maybe a position, function of position. And then the last one is the volume charge, and then we'll look at an example. Here, the charge is spread over volume, QdV, and has units of coulombs per meter cubed. The total charge is now integration over volume, and the electric field we get by integrating over the volume 1 over 4 pi epsilon. And same integrand in all three cases, only differing in whether we're integrating over a line, a surface, or a volume. Rho V, point dV. Okay, so what's surprising, I think, about these equations is that they can be solved at all. And usually you can only use these equations to find the electric field for very special cases. Otherwise, we'd have to resort to numerical integration programs to actually evaluate the field at certain points. So find the electric field due to an infinite line charge of constant density here, rho L, along the z-axis. So this is a classic problem in electromagnetics. What's the electric field here? And so here, X, Y, Z. Here we've got this thing is actually infinite. I'm showing just a section of it here. And an arbitrary point in space is what we're calling R, our R vector. And then this R prime is a position vector to an elemental length dl segment of this line charge. Now, a problem you're faced with here, and all these is, what's the best coordinate system to do this integration in? And you could use any, but my recommendation is use the coordinate system that results in the fewest number of variables. Now here, I got this infinite line along the z-axis. Now, if you're an observer at some field point here, I'm going to see exactly the same picture no matter what angle I'm at around this thing, right? You know, if it's, you know, in the vast universe, it's just me and this line charge. Doesn't matter what my angle is around this thing, I'm going to see exactly the same picture. Doesn't matter what my height is, this thing is infinitely long. So that means when I look up, I see an infinitely long line charge. I look down, I see an infinitely long line charge. Doesn't matter what my height is above the XY plane, I see the same picture. So the cylindrical coordinate system is the easiest to use here. I'll just set up the integral, and we'll look at this next time. It's 1 over 4 pi epsilon, integral from minus infinity to infinity. Now my R vector here in cylindrical components is rho hat plus z hat, and my R prime vector is just z hat z. That's my vector to an elemental, a DL element. Again, it automatically takes into account the sign, because if the element is below the XY plane, I'll have a minus c there. And then, so what I have here is rho hat rho plus z hat z minus z prime over, I have rho hat rho plus z hat z minus z prime cubed rho L dz. And we have to integrate this over minus infinity. Okay, so the approach, we'll finish this next time. That magnitude, that will become, rho squared plus z minus z prime to the 3 halves. And I'll break this up into a rho hat component, a z hat component, and then we can actually carry out those integrals and see what the resulting field is. And it simplifies a lot. As you might expect, it's just going to have a rho hat actually directed component, but we'll look at that next time when we finish that problem. Yeah.
Why is on the integral for line charge, why is it